Okay, welcome to chapter 4. This is water using our planet to quench our thirst. So, in this chapter, we're going to discuss we need water to live. We're humans, all living things need water to live. And the problem is that as you'll see in this chapter, is that fresh, clean water is a very highly sought after commodity, and there's actually not as much on Earth as you think there is. So we're going to discuss in this chapter what's being done with water, both good and bad, looking at different ways to sustain our water system and some innovative solutions near the end for sustainability, especially helping those who don't have access to clean water. There's a lot of stuff in this chapter. Hopefully you'll find it useful. I learned a lot as well. I knew some of this stuff just being in the geosciences, but I think it's a pretty cool chapter. Let's get going. So you can't talk about water without understanding sort of the science behind it a little bit. And the term is called hydrology, which is the movement of water. It's the study of the movement, distribution, and the quality of water within the earth. Now, we have people in my department at University of Wisconsin-Milwaukee who do this very thing. We have some that kind of specialize in how crops grow. We have some that specialize in the chemistry of what's underground, and other ones that sort of model as how water's going to move and where it's going to be and all kinds of things. Groundwater studies or hydrology studies in the geosciences is a huge, huge aspect, and a lot of our students end up going to this field. Now, most of the drinkable water on Earth is stored as what's called groundwater, so we don't even see it. It's deep underground. So if you live in an area where you have well water, let's say outside the city somewhere, you're pulling that water out of a well that's sitting way down deep in the ground where the water's able to flow through certain rock layers. And we'll talk more about that as we go. Um, but the idea is that the hydrology kind of encompasses how that water got there. You can look at, in the slide here, you can see in this green area up here, you have evaporation. So the sun heats up the air. The air has water in it, and it evaporates up into the air. Or excuse me, the sun heats the water on the ground and creates water vapor that goes up into the air. It then condenses back into water droplets, which then comes down as precipitation. All right. That precipitation becomes surface runoff. The water's got to go somewhere when it hits the ground, right? And then it's going through, all other the kinds of other interceptions where it could be going into a stormwater system. It could be going back into the soil. It could be going into a river or a lake. And then the whole cycle starts to rotate again, to go through it again. So then you have transpiration where it's taking that water and utilizing it for things like crops, infiltration into the soil, and then subsurface runoff, which is down below the ground, and you have water in the rock or in the soil that's being able to move around. And that all of these play a role in the science of hydrology. Now, if you look at the stat here, only 1% of all of the fresh water on Earth is stored at the surface. Think about that. Only 1% of the water, fresh water that is drinkable, is stored at the surface of the Earth. That means the rest of it is to be tied up somewhere, and we're going to talk about that in the next slide. So where is Earth's water? Well, hopefully you could see right away. The bulk majority of it, 96.5 of all of the water on Earth is stored in the oceans. Okay, that makes sense. We're the blue planet. You know, all 70% of the Earth's surface is covered with water, and then those oceans are very, very deep. So absolutely almost all of the water is tied up in the oceans. However, of that, there's an extra 2.5% sitting here at the top, and of that 2.5%, 68% of the fresh water is tied up in glaciers and ice caps. So again, we don't have access to it. It's either at the North Pole or the South Pole, and a lot of that is melting with global climate change and everything. Then you have 30% stored in groundwater. Now, this is the water that's being moved around underground in rock layers that allow the water to move. We call that permeable. So they have little holes, what we call it's porous, the little holes that allow the water to flow through it over time. So when rainwater comes down and does go through the soils and everything, some of that water, a lot of that water does get down into the groundwater system. And we'll talk about this a little bit later in this chapter, things like wetlands. That's why wetlands are so important. Think of a swamp, right? You have a swamp sitting there with all of this water sitting on the surface. Well, that water is slowly trickling down through the soil, through the, and it eventually makes its way down into the groundwater system. So that's a hugely important. We'll talk about that more later. And then finally, you have 1.2% of surface freshwater. Now, up here in the upper Great Lakes where we live, we see Lake Michigan, or you think of all the other Great Lakes. Wow, look at all that water. That's true. It's one of the largest freshwater systems in the world. However, only 1.2% worldwide is stored at the surface in lakes and rivers and things like that. It's a very, very, very small portion of the surface groundwater. Now let's break down that 1.2%. Ground ice and permafrost. So most of that fresh water at the surface is frozen up near the polar regions or down near the polar regions. So that water is stored in the soil. Think of it. If you go out in the dead of winter here in Wisconsin and take a shovel and dig up some ground, right? That ground is going to be hard as a rock. Why? Because there's water in there and that water froze. Okay. So a lot of this tiny sliver of 1.2% of the water is stored as frozen ground. Okay. And then finally, you get all of this other stuff up here. You have 20%, which is lakes. We have the Great Lakes, and then soil moisture, swamps, marshes, things like that. So hopefully you could see from this diagram that of the water available to humans, it's very, very small percentage. You have 1.2% of the fresh water at the surface, while over half of that is frozen in the ground. So we have even less than that available to humans for consumption for things like, water bathing, what we do every day here. We'll talk about that um, more as we go. So hopefully you can see right away that water is a vital resource. And we've done a lot of damage to the water supply system, only speaking of in America, but worldwide, it's not very good. It's not a very pleasant scene. So let's take a quick look at what's called the hydrologic cycle. So how is this water getting to where it needs to go? And there, like I said, I mentioned it a little bit before. You have things like the sun heats up the ground, right? You have things like evaporation. So you have, let's say, an ocean. That ocean water is evaporated, and then the evaporation goes back up into the clouds and then condenses and forms clouds. When the clouds get too heavy with the amount of condensation in there, it comes down as rain or precipitation. That rain comes down and gets transported onto the ground and has several places it can go. It can run, downhill into a stream. It can go down into the ground and into groundwater. It could come down as snow onto a mountain, right? However, you also have what's called transpiration. You have things that go back up, like evaporation and evapotranspiration, which is the plants giving off their sort of energy here. So it goes around and around and around. The problem is that we as humans require more and more and more water. There's 7 billion people on Earth, and with all of everything else, and you'll see this as we go through this chapter, all of these things play a role in how much water is being used. So if the water is being used faster than it can get back into the system, we have things like water scarcity issues. Again, it seems foreign to us here in the upper Midwest because we have Lake Michigan sitting right there. But in other parts of the country, you go down to the desert Southwest and places like Phoenix and California, you know, a lot of people forget LA is it's a sub-desert. It's a desert, almost a desert climate, and they are running out of water in California like crazy. There's too many people, too many things that are just drawing up all that water. So they have huge water issues in California because this cycle isn't allowed to sort of keep itself going because we're sucking it up faster than it can be regenerated. So again, why is this happening? Well, you can see it in the picture. People. There's a lot of people. And you got about 7.3 billion people, and we need to be able to figure out ways to sustain the water consumption that's going on. All right. And the unfortunate reality is some of the largest or the areas growing the fastest are those areas that have not necessarily the most economically viable economies. So, poor nations are growing at a faster rate than the more developed countries. And that's a huge issue because you take more people and put them in an area that has even less water, you're bound to have water issues. And then there's this concept of water footprint. So it's kind of like your carbon footprint, but with water. Maybe you've heard of carbon footprint. It's the amount of water per capita. How much does the average human use in a day? And here in America, we are very wasteful. There's no ifs, ands, or buts about it. We'll talk about some of that as we go along. But we as Americans take water for granted. We always have it. It's almost always there. Um, but we're also very wasteful. So that's what this water footprint idea is, kind of like your carbon footprint with, how much you drive and all this other stuff. And there, because of the population explosion in certain areas, and just by the mere fact that some areas have more water available to them than others, there are inequity issues between developed nations like the US and developing nations, let's say like somewhere in Africa. Okay, those countries are having issues because their economy can't sustain things. And again, we'll talk a little bit more about that as we go along. But you have a bad combination of population explosion with not enough water resources to handle that population. And then another part of that is the urbanization of the world. I mean, this is a worldwide thing where people are flocking to the cities. They're leaving the rural areas and flocking to the cities. So that creates a consumption issue in the sense that you have to have more water for more people in a given area. But because of having more people in that area, you also have more pollution. So it's sort of this bad cycle of more people, more pollution, more people, more pollution. And the problem is in all of that, the water isn't being added fast enough to the system. We're sucking it too fast, so to speak. So one of the largest consumers of water is agricultural worldwide. It's 70% of all of the world water being used in the world is used for agriculture. Well, humans need to eat, right? But within that, there's also some really crazy numbers in terms of things like how much water it takes for one head of cattle. This is why some people really push for a vegan diet because it's a lot less stressful on the environment, which I get to a point, but I like my burgers. So, um, raising cattle takes a ton of water. Raising certain crops, there's other crops like rice. Rice is one of the most grown crops in the world. Just think of, Japan and China and all those places, they rely heavily on rice. Well, rice requires a ton of water to grow. It's essentially grown in a marsh. You have to have a lot of water to grow rice, alfalfa, cotton, and almonds. Hopefully you read the book. I'm going to kind of reiterate something in the book that I did not know, that it actually takes more water to create what was that, a liter of almond milk than it does cow milk, because almonds, the almond trees suck up so much water, and then there's the processing of the almonds to get at the almond milk. It actually takes a bit more water to produce almond milk than cow's milk, and that blew me away. I did not know that. I've never even had almond milk. I don't know what it tastes like. I know for people who are lactose intolerant, it's a great thing, but I've never personally had it. But that really blew me away that's actually the case. And you'll see that as we go, that certain ideas seem good on the surface, but end up using more energy than they actually are supposed to um, uh, lessen. So they use more energy than, than what they were designed to be used for. Another huge user of water is industry and energy. Okay, so things like mining coal uses a boatload of water. They use it both for extraction, and then I mentioned this, I believe, in the last chapter. They spray the mines down. They spray it, the roads down to keep the dust down. So they're constantly using water. And in fact, there's other ore minerals, things like gold and stuff like that, that use even more water because of the extraction process than, let's say, coal. Unfortunately, it's this, they call it this water energy nexus, the relationship between how much water is used to generate and transmit energy and how much it takes to collect, clean, remove, store, and deposit it. And that's exactly what I just mentioned in the last slide. Sometimes it takes more energy to actually create the thing that's supposed to save energy. That is a little bit of the argument right now with things like electric cars. Electric cars, the batteries that go in electric cars require a ton of energy to create. Not to mention they have a lot of nasty stuff in them. I'm sure over time that'll get better and better and better, but right now that stuff, those batteries, they take quite a bit of energy to create. The textiles. This is another thing that blew me away. Textiles. Um, it takes almost 2,000 gallons of water to create one pair of jeans. Think about that. You see piles of jeans at the stores. You go to all these stores that carry jeans because of they have to use dyes and stuff like that in their jean making process. I'm like, wow, it really makes you think about the clothes you wear and everything. And about 40,000 gallons of water to produce the average car, including the tires that are on there. Think about that. One car, 40,000 gallons. And how many cars do they make? I mean, they're rolling off the assembly line constantly. That's mind-boggling how much water that is. So you could see sort of in the image on the right here, or excuse me, on the left, is the car assembly line. Hopefully you've seen that before. The one on the right over here is the coal extraction. I know they're a little covered up, but that's okay. And then the one in the middle is one of those big vats with blue dye that is used to create jeans. So I had to put that in there. I know I'm covering it up a little bit, but you get the idea. It's a lot of water being used by the production of energy and then industrial uses. Well, you can't talk about water and the water issues if you're not going to talk about water pollution. And water pollution is a huge topic. It's gotten better, and you'll see that as we go through this. Um, when you compare it to 40, 50 years ago, compared today, it's gotten a ton better, at least in America. Okay, we can only speak for America because we've enacted laws and things, and we'll talk about that. But worldwide, it's still a major, major, major problem. So you have things like point source solution, and these are, you know, pipes that come out of, you could see there, pipes coming out of industrial factories or treatment plants or sewers and things like that. So um, those are directly aligned right out of a manufacturing plant right into, let's say, a river or a stream kind of thing. Um, and that is what is mostly governed by the EPA is point source pollution. So they can go, okay, that pipe is putting out this contamination from that building, and they know exactly who's responsible for it. Okay, and we'll talk about the other one, which you can kind of see in that as well, what are called non-point source pollutions. And those are a bit trickier. And unfortunately, those are a huge issue because there's really no jurisdiction for them. So non-point source solution is caused when rainfall, snowmelt, you know, move over the ground and picks up and carries things with it. And then it gets into things like the water gets deposited into lakes, rivers, wetlands, coastal waters. So storm drains, you could see on the image on the left, sort of, that's a huge agricultural field. Well, what do they use on agriculture? If it's not organic, they're using things like pesticides and herbicides and things to help make it grow, chemicals to help make it grow. When it rains, those chemicals get washed off and then they get carried. You can see all the mud here, this sediment, which we'll talk about in a second, everything that's been contaminated gets washed away into the local rivers, storm drains, and it has to go somewhere. Now, this is a very huge problem because, again, you can't pinpoint where it's coming from. You can't go to that farmer and say, well, you're responsible for this much because you don't know how much it is. So the non-point point source pollution is a very sort of gray area, unfortunately, and it's really not governed by the EPA, the Environmental Protection Agency, again, because they can't pinpoint where it's coming from. There's no way to place blame, so to speak, on who might be creating these non-point source pollution um, contaminations. So another huge problem with water pollution are what are called pathogenic pollutants. Pathogenic pollutants are, in a nutshell, caused by fecal matter. Okay, I'm not going to go into the gory details, but we're talking about poop here. Okay, everything, every animal, every human has waste, and that waste has to go somewhere. The problem is at least in our country, we have pretty good systems for that to handle that, but it doesn't always work. In other areas of the world, they don't have sewer systems. They don't have these, municipal, water treatment plants that can help get rid of what are called pathogens. And pathogens are things that can they're like biological critters, so to speak, that can really harm you can get typhoid fever, cholera, hepatitis A, and a ton of diarrhea causing pathogens. So this stuff gets in your stomach, and it's not a good idea. Now, I don't know if any of you are old enough to remember this, but back in 1993, Milwaukee got hit with what's called cryptosporidium. Now, that's a pathogen, and it got into the water system. However, the problem was when people were first getting sick, they told people, because the diarrhea was so bad, they told people to stay hydrated, keep drinking water, keep drinking water, keep drinking water. But they didn't realize is the water is what was causing it. I had it. It was brutal. I'm not going to go into the details. Just trust me. You couldn't be more than 3 feet from a bathroom. You had to be. It was nonstop for days until they finally realized that you had to boil your water off. Boil water to kill off, and you could drink the boiled water, distilled water. It was really bad. It was horrible. So that was something that you don't expect here in America, right? But it happened. Go look it up. Cryptosporidium outbreak. I believe it was 1993. I want to say. Um, and if you look at this stat here, more than 2.5 billion people do not have access to toilets or latrines. Okay, that's crazy. 2.5 billion people don't have basic sanitary conditions. And that's why there's areas of the world that have huge outbreaks of things like cholera or these typhoid, because they're essentially drinking from the same water that people are using as a sewer. And as gross as that sounds, that's what's happening. Um, Now you have sewage, which is kind of different. That's the polluted rainwater, domestic sewage that we and industrial waste that we produce every day, and that water goes to the treatment plants. But again, like the cryptosporidium, something was missed there, and uh, all of a sudden you have this huge outbreak. Now there are we have what are called combined sewer systems here in Milwaukee, and every once in a while, if it rains too much and all that, you'll get a release of sewage into Lake Michigan. I think I have a slide on that coming up here in a second, so I'm not going to dwell on that now. But it's not always fun, and there are the sewage sometimes comes from ships. The ships have people on them, and those people, they have waste, and then the ships take that waste and they just dump it into whatever body of water that they're in. Kind of gross, but that's what happens. And then obviously livestock is a huge, huge issue. If you have large farms with cattle, you're going to get large amounts of poop, right? That and then where are they going? They're just going on the ground. Then it rains and bits and pieces of that get put in back into the water system. It's a huge issue. And in fact, now that they have limits, in terms of uh, what are called CAFO farms. CAFO, I forgot that. If you have a certain amount of cattle, you have to take certain measures to make sure that that runoff and the pollution created by all of the fecal matter isn't going to be an issue. I had a student in one of my classes do a GIS project on this. That's not important. I'm just saying these type of farms are all over the country, but in Wisconsin, once you have so many livestock or so many heads of cattle, you're playing by a different set of rules to make sure that um, these pathogenic pollutants don't become an issue. Another major issue for our water supply systems is what is chemical pollution. So we talked about sort of the natural pollution that occurs, from human waste or animal waste, and that is a massive issue. But there's also blatant chemicals that are being put into the water system from things like manufacturing and you saw those pipes earlier. A lot of this stuff is just, especially long ago, it was just getting put right back into our water system. Now, the picture on the upper right there is actually from England, but kind of shows you how nasty things can get. And again, in America, it's still like this in places. Don't get me wrong, but there are many more rules in place, and it has gotten a lot better. The water as a whole in our country's gotten a lot better. But you could see, there's oil in the water. There's all kinds of weird contaminated or contamination chemicals that you probably have never even heard of that are in that water besides just, let's say, oil or hydrocarbons. So chemical pollution are just toxic chemicals that get put in to the water system via some type of industry or agriculture or transportation. Cars leak, trains leak, planes leak. All of these things get put into, they fall into the ground and eventually get washed into the storm water. um, we use things like lawn pesticides and fertilizers, and all of these things get put into the water system. And once they're in the water system, whether it be municipal or an aquatic, a natural aquatic system, if it's in the municipal system, some of that stuff can be removed. Not all of it, but some of it. And if it gets into a naturally occurring aquatic system, those chemicals can start to wreak havoc on the natural system. It could either create a situation that it just literally kills off the fish, or we talked about it a while back, that eutrophication, where all of a sudden you get all this algae that basically chokes off the oxygen, which then chokes off the fish. Um, and one of the things that a lot of people don't realize is that the distribution systems, the sewers and all the pipes, a lot of that stuff was put into place years ago. Way back when cities were first being formed, the sewers were being put in, and the water lines, all of those things. So the distribution centers or systems themselves are really old. And that creates another issue with things like lead in pipes, from old soldering and things like that. And you hear about this all the time. There was a massive issue in Flint, Michigan, you know, the Flint River, or Flint, Michigan, where this was only like 6 years ago, where something like 12,000 kids were exposed to really high levels of lead poisoning from the drinking water, because they decided to stop using the water that they had been using and use the Flint River water, and they didn't clean it up well enough. So it's a huge lawsuit. It's huge, it causes all kinds of health issues. And another thing is naturally occurring arsenic. Now, if you don't know what arsenic is, its common name is rat poison. All right, and it can get into it's found naturally in the ground, And the problem is in areas that have high levels of arsenic, it can also get into the water system and cause massive health issues, neurological. It can cause, all kinds of crazy stuff. And again, that's not being added by man. That's just naturally occurring. So these types of issues, these chemical pollutions, other than the arsenic one, they can be they can be fixed. They can, with the right systems. The problem is it all comes down to money, of course. And because the distribution centers are so old, um, a lot of places can't handle it. And I use Milwaukee as an example. We have the deep tunnel sewer. The problem with that is it fills up really quickly because we have a combined system, meaning every time you flush your toilet, it's going into the same system as every time the water drains down the side of your house. So the pipes become overloaded, which means the sewer fills up, which means the water treatment plant can't handle it, and then it gets released almost completely untreated into Lake Michigan. And now, luckily, that only happens once or twice a year, but it's still bad and it shouldn't happen at all. But nobody wants to pay the bill to have the sewer systems separated, one into, sort of the septic system and then one into a rainwater system. There's also this thing called thermal pollution. Now, this is a bit more specific, but it is actually, if you have any type of nuclear reactors that are generating energy, um, one of the pollutants, so to speak, for nuclear reactors is highly um, thermal, hot water being introduced back into the system because they're creating steam. Well, that hot water has to go somewhere, and they pump it back into the body of water that they got it from. This happens right in Lake Michigan. It happens all over the country, and that hot thermal water creates other issues in terms of it'll kill off fish because the fish can't breathe in that kind of water. It becomes not oxygenated enough. There's not enough oxygen. You alter the food web because of this, and you get things like algal blooms. That you could see that in these green blobs here, just like we saw in the Chesapeake Bay slide I showed you a couple chapters ago. That highly warm water creates a situation where things can grow really fast, but those things that are growing really fast are not the things you want growing at all in that particular ecosystem, like the algae. The algae then uh, create a low dissolved oxygen here. It creates low dissolved oxygen, which then kills off the fish. So, although thermal pollution isn't as big of an issue because it's a highly localized one, if you have a nuclear reactor, a nuclear energy reactor there, it is an issue around them, and that's one of those things where it's highly regulated, but it still has to be. It's a necessary evil, so to speak. If you have the nuclear reactor, that warm water has to go somewhere. Typically, what they do now is they take those pipes, like let's say in Lake Michigan, and they extend them way offshore into deep water where it'll cool off very quickly, and there's typically not as many fish. So another important part of water is the fact that it's a commodity. It can be bought and sold. And because of this, that creates another series of issues in terms of water equity again. Who has the rights to the water? And water rights have been an issue for like a thousands of years. And you'll see some of that as we go. It's created military battles over who has control over the water. So, water is a commodity. It's a resource and a commodity because we as humans have to have it. And because we have to have it, somebody wants to sell it to you, which then makes it a commodity. So let's look at bottled water. Here I have one right here. Okay. The bottled water market reached $200 billion in 2017. I'm old enough to remember when they first started selling bottled water, going, why the heck would anybody buy bottled water? I don't buy, I'll be perfectly honest with you. This is the absolute honest to God truth. You see this bottle here, this is a Voss bottle. I actually don't like bottled water, but I like the convenience of having the bottle. All right. And I know this is weird. So we buy bottled water because my kids drink almost water exclusively. Neither one of my kids drinks soda almost at all. Don't ask me why. but we reuse them. We fill them up, and I'll throw them away eventually, but we refill them. And I know a lot of people say, "Oh, you shouldn't do that." We've been doing it for years. It's not a big deal. But I actually don't like the taste of bottled water. I hate it. I prefer what we have coming out of our tap. If you've lived, I lived in St. Louis for a couple of years, and they're drinking Mississippi River mud water that on the hottest day will never get cold. It's just their water's nasty. It's over chlorinated to get rid of everything because it's river water, and because it's river water, it's at the surface and it just never gets cold. So I just prefer having a bottle of water that I can get cold quick. I prefer tap water. There's a few bottled waters that aren't bad. Fiji's not bad, Voss is not bad, but most of the other ones I hate. I prefer just tap water. So, but the dirty little secret of this is that a lot of the popular brands have chemicals in them. A lot of it's just recycled, recirculated tap water. There's nothing special about it. It's all marketing, especially the ones like Dasani, the Nestle products, anything owned by a bigger company. All of those are just basically tap water that have been probably cleaned and then reintroduced other minerals in it. Some of them haven't been cleaned, and they have sometimes they've found above acceptable levels of these pollutants in them, the bottled water you're buying. And then you have the issue of, as you can see in the picture here, the bottles themselves. And even me, I'm an avid recycler. I try to recycle as much as I can. I'm not even sure what plastics are and what plastics aren't recyclable. So I just throw it all in the green bin and let them figure it out. All right. However, making and transporting the water costs more, requires more energy and fossil fuels and greenhouse gases, excuse me, that it's crazy. So you're actually doing more harm to the environment by buying these bottled waters because it takes so much energy to both make the bottles, fill the bottles, and then distribute the bottles. And then you got to know, what are we going to do with the bottles? And I showed this picture here of the bottles floating in the water. If you look this up, and all I did is put bottled water or environment, I did a Google search, and there's mountains of these things, mountains of bottled waters. It's and man, it's crazy. And I'm guilty. I'm totally guilty. And you got to ask yourself, are you guilty too? You probably are. And it's not just bottled water. I mean, soda bottles and everything else too. But it's become a real big deal. And I see people um, at the stores who buy two, three, big cases of bottled water, and I'll buy one every couple months because again, we refill them, and then after a while, you probably want to replace them. But I'm not doing it all the time, and I do it for convenience for my kids. And I always try to make sure to recycle them, that they don't get thrown away. But bottled water is a big issue, but there's too much money to be had, as you can see in that number, $200 billion. Makes me want to start a bottled water company. And then finally, the last little bullet point there, you got air, and I read this in the book. There's wells in California that have run dry. So Nestle, the company Nestle, who it's a big conglomerate. It's not just Nestle Crunch bars. Um, they are actually selling back the water that they used at an inflated price, which is total BS. But you know, it's a market-driven commodity. That's the whole point of this. So just try to keep that in mind next time you buy a bottle of water. I'm not trying to guilt you. I will still buy bottled water if it's convenient for me. But at home, I refill them. Or I just drink out of a glass. But there's many times where you just want that water on the go, and it's just easier to grab a bottle. But it's an interesting quandary because it's so ingrained now with bottled water. You see it if you go to the grocery store, and no one realizes that the issues it's actually causing. Another, and I mentioned this briefly, another sort of water commodity issue is water conflicts. Water doesn't care about political boundaries. A river's going to flow where the river's going to flow, and who decides where that the water starts and stops is that's a political thing. Um, Rivers, lakes, and watersheds span multiple countries, counties, causing all kinds of tension, including military disputes. So the picture you see on the left there is of the Jordan River in the Middle East. That river flows through much of the Middle East, and the Middle East has always been, tense, with conflicts between Israel and Palestine and Syria and all of those countries. And I'm not going into any of that. The point is part of that is water. The Colorado River here in America is so heavily dammed and used that by the time it reaches Mexico, there's almost nothing left of it. And Mexico has been trying to sue us, I think, if I'm not mistaken, trying to sue us pretty much saying, hey, you're using up all the water, open it up a bit more. And a lot of that water from the Colorado River is going straight over to Phoenix and straight over to LA because those are huge urban centers that require a lot of water. And they're both, yep, in deserts. So there's not a lot of water to be had in those areas. So, just the mere fact that a river flows through multiple countries, everybody wants the water, they need the water, but it can create issues, including military conflicts. So how does water issues impact ecosystems? We can't talk about water issues without talking about how it's affecting, the natural environment around it. And there's, we've already talked about the pollution aspect of it, right? There's both the human, the pathogens, there's chemical, there's, water runoff in, excuse me. But how is it actually affecting? What types of issues are arising because of everything going on in these? Well, when it comes to rivers, one of the big issues is sedimentation. So we talked about this with the non-point source pollution, things like runoff from agricultural fields. Well, all of that runoff has to go somewhere. And when it reaches a river or a body of water, the particles, the tiny little particles that are in solution, what we call solution, they've been dissolved into the water, so to speak, they're carried along with the river or into a lake, and then they settle. They trickle down to the bottom of that particular water body, creating a solid layer. The problem becomes is when you have too much sediment. That too much sediment can choke off and create serious issues for an aquatic ecosystem. It's one of the reasons, partly one of the reasons. So the Mississippi River is one of the most used rivers in the world, right? So the Army Corps of Engineers are constantly making sure they're dredging out the channels, making sure the ships can get through, and then they built the locks and dams, things like that. The problem with that is it disrupts the natural flow of the river, creating other issues like sediment buildup. We see this too in Lake Michigan. If you look at an aerial view of Lake Michigan has what's called longshore drift. So the prevailing winds are out of the north northeast, so the waves don't hit the shore at perfect sideways, right? They hit them from an angle. I don't know if you can see that. They hit them from an angle. And when they hit them from an angle, if there's anything sticking out into the water, let's say a pier or some type of rock wall, though that angle has it, what happens is you get sediment buildup, and you can actually create what are called jetties and these big sand islands just because the sediment has nowhere to go. Now, these sediments come from erosion from agriculture, forestry, construction, and mining. And along with that, unfortunately, is a lot of pollutants. Think of, agriculture again with pesticides, herbicides, forestry. It could just be, anything runoff from a forest, and within that, maybe there's natural pollution. And then obviously construction, it creates a lot of dust, and mining, which we've already talked about. Mining is a huge, huge issue for this type of thing because they create tons and tons of sediment dust, from all of even from the parts that aren't being used, what's called the tailings. Now, this sediment, when it starts to filter down and create this layer on the bottom, if you have little critters and organisms that live on the bottom, they're just going to get buried. All right, and it damages them because they can't move very well. They live off the bottom, and if they're being covered up, they're essentially being buried alive, so to speak. Then you can, like you can see in that picture, look at all that brown mud coming out of that particular river. Think about if you were a fish. How do you breathe in that? That can really start to damage like fish gills and stuff like that because the water's so cemented, or excuse me, heavily has a ton of sediment in it that it starts to damage the. I mean, fish gills are very fragile because they're designed to filter out the oxygen so they can breathe. You know, we don't like having anything foreign in our lungs, right? When you're breathing, you just want normal air. So it's no different for a fish. And if you have all this stuff suspended in the water, it can start to cause damage to the fish over time. So that picture on the left is a really good example of how all that sediment coming off a river starts to have an interplay with, let's say, a deeper body of water. And you can see that clear delineation between where the sediment stops and then the water begins, so to speak, the clean water. And it's like this everywhere. That where the Amazon comes out, any major river, the Mississippi, the Nile, you can go look on Google Earth and see this all over the world. It's very common. The problem is because of all of the agriculture and cattle farming and all this, what was once a natural process is now a natural process that's also carrying along with it a ton of pollutants. Another huge ecosystem issue is the building of dams. Now, dams are built mainly for power generation. Um, and so the water flows through the dam. It turns it turns turbines, which create steam and then electricity. That's what dams are for mostly. Now, sometimes they're used for flood control, but most of them are used for power generation, all the big ones. And what you see in the pictures, hopefully you've recognized the upper left or upper right corner is the Hoover Dam in Arizona. And then the lower one is one of the largest dams in the world. That's the Three Gorges Dam in China. And I wanted to make sure I included that. I know I'm covering it up a little bit. I wanted to include that because they've had nothing but issues with that dam since it was put online. That is a huge dam, huge dam compared to almost anything else in the world. And it's crazy. So dams are obstructions, right? So you're taking the natural flow of a river and you're altering it by creating a dam. The water's still going through, but it's regulated so they could generate power, right? Well, what happens downriver and upriver is dictated by that obstruction. So downriver is usually flood control because, they're only allowing so much water out at a time. So, but upriver, you also have these massive lakes that are created behind them. Like in the Hoover Dam, this is Lake Mead, right? And up here, I don't know what they call this, but this lake is massive. Again, that's the largest dam in the world, I believe. Now, there's other negative impacts such as the riverbed is changed. Again, the sedimentation changes. So anything that's sort of crawling around on the bottom, they're going to get more sediment and probably get buried because they can't move around very much. That's their home. These little critters that are on the bottom. And again, fish feed off those. So if those die, the fish die. There's too much sediment. It's just this nasty cycle. Now, there's also the social impacts of dams in addition to sort of the natural ecosystems. And I'm kind of glossing over the ecosystem part a little bit because there's a lot more to it than that. And I can't go into all of it right now. But, when you have these massive lakes being built that are being created behind a dam, they create all kinds of issues, slope instabilities where it can create like rock falls or landslides. You create enormous hardships, which we'll get to in a second. Um, and just the overall stress on everything because you're creating this massive lake where there never was once before. Now, the bottom bullet point is another huge uh, aspect to this that isn't talked about a lot. China is China, right? It's a communist country, and the government pretty much tells you what to do, so to speak. When they built these dams, millions of people mostly poor and indigenous people. So people that have only lived there their whole lives were forced to move in order for this dam to be built. Look at that, millions. So that Three Gorges Dam, I think that, I think that they said in the book or something like that, it displaced anywhere from 80,000 to 250,000 people. Just that one dam, they made those people move because the lake that was gonna fill up behind it would have put their entire village or city underwater. Think about that. I mean, it's just mind-boggling that when I was getting the images for the Three Gorges Dam, I read a few things and kind of going down the rabbit's hole on Google. I didn't know this because it's not the kind of thing you hear about in the news a lot, but they're already contemplating blowing the whole thing up. It's caused so many issues, both structurally, and there's been floods downriver that have killed thousands. It's a big mess. This Three Gorges Dam in China is a huge mess. Loss of wetlands is another crucial aspect to the water scarcity in certain areas and making sure that the aquatic ecosystems stay sort of in balance. So, wetland is an area where water covers the soil all year or at least most of the year. Think of this as swamps, marshes, stuff like that. These play a huge role in maintaining ecosystems both in freshwater and saltwater because of the aquatic and terrestrial, like on land life that occurs within them. They form a huge ecosystem, and tons of species live within these wetlands. There's a number in the book about like something like, I don't know, 40% or something. I can't remember. I don't want to make it up. Um, but one of the things that's so important with wetlands is they soak up rain. Okay. It rains and rains and rains, and you have all this standing water, and it's not the kind of place you want to necessarily hang out with. And probably mosquitoes and maybe alligators, whatever. But it's a hugely important air, because though that water that's sitting in there over time soaks down and replenishes the groundwater system and filters out the pollution. How does it do that? Well, the water is actually moving through these wetlands very slowly. You can't see it, but it does over long periods of time. And all of the soil that it sits on and all the rock beneath it over time start to filter out those pollutants. It's one of the only natural pollutant filters there is. I mean, we could do it we have man-made systems to do that, but in nature, A, it takes a lot longer, and B, you have to have the right system to do this. And wetlands are exactly that's their job. They provide an amazing habitat for tons of animals and fish and aquatic life, but that water plays a role again in making sure that other areas, let's say down slope, so to speak, have water for the future. Not only just water, but clean water. So the problem with with the loss of wetlands, is a lot of areas that have them end up digging it up so they can plant things like crops and stuff like that, which then the water's not sitting there, so it's not replenishing the groundwater system. This is an issue, is kind of like deforestation, where you're not necessarily chopping down all the trees, which causes issues with both surface and then obviously the photosynthesis of getting carbon dioxide out of the atmosphere. But it's the same sort of thing where when you get rid of the wetlands, you're getting rid of not only habitats for tons of little critters, but you're also getting rid of Earth's ability to regenerate its own water system. And again, a lot of times this is done because the soils that these sit in are very rich and really good for agriculture, and people know that. So they drain them. They'll figure out where the natural drainage point is, just like a plug in a tub, right? You take out the plug, the water drains out. Well, the same thing applies with wetlands. If you find the area that will flow down slope, they'll just sort of dig a ditch, and the whole thing will start to drain away, leaving behind all of this rich soil. The problem is you just wiped out an entire ecosystem and the ability of the earth to regenerate its groundwater. Watershed management is a crucial aspect to maintaining the groundwater within and all of the ground and surface water within a given area. So a watershed is an area of land that drains all the streams, rainfall, and to a common outlet such as a reservoir or a mouth of a bay or a stream channel. So everything within a particular region kind of flows into this area, and that's how we designate a watershed. Now, the reason why this is important is because maintaining watershed maintenance allows people who study that kind of thing to figure out, okay, what's going where's the water coming from, where is it going, but also those like non-point and point source pollutions, where are they coming from based upon other factors within that particular watershed. So watersheds capture the precipitation, filter, and store water. All right. Now, when you have a bunch of these underground, so to speak, now this is a little bit different than an aquifer. All right, so there's an aquifer here in the middle of the country called the Ogallala. It's somewhere in this area, and it's huge. It's one of the largest underground aquifers in the country. If it might be the biggest. And all of these watersheds play a role in making sure that the Ogallala gets regenerated. Why is that a big deal? Because the Ogallala is one of the most used aquifers for agriculture throughout the Great Plains. It covers much of the Great Plains, and there's a ton of irrigation that from water that's being pumped out of that aquifer, way faster than it could probably, way faster than it's being um, regenerated. And that's the little thing there. Over pumping the water is a major issue. Um, because again, the earth doesn't work on human timescales. The earth is a very slow process, so it takes a long time for all that rainwater and everything to seep down back into that system. Now, unfortunately, with all of the with all the farms and the irrigation, there's good irrigation and bad irrigation, so to speak. We'll talk about that in a bit. Along with deforestation, which does deforestation allows the water to run away much quicker as opposed to being kind of locked in. That's why deforestation is bad for water regeneration. It doesn't allow the water to seep down into the ground as quick. It kind of runs off much faster if you don't have things like root systems and stuff like that to help slow it down. Another problem, not necessarily in this area, but down in Florida especially, okay, down in that area, is what's called saltwater intrusion. So there's a lot of people in Florida. A lot of people move to Florida from all over the country. And the thing with Florida is only a couple of feet above sea level. They have a ton of water just underneath the surface. There's a lot of water under Florida, fresh water. The problem is they're pumping it so fast that it's sucking in salt water from the oceans, and you create what's called saltwater intrusion. The last thing you want in your well or in your municipal water is salt, because once it's in there, it's hard to get rid of and it causes all kinds of health issues. You cannot drink salt water. You will get bad health problems. And once a well, let's say a municipal well, is contaminated, that well is done. You can't get rid of it. So, over pumping in areas where saltwater intrusion might take place is a huge issue. Now, there have been many policies that have been enacted over the years to help clean up the water. Now, we talked last chapter about the Clean Air Act, which made huge strides in reducing the amount of smoggy days, especially over in metropolitan areas. The other one is the Clean Water Act that began all the way back in 1948, but was really enacted in 1972. Um, I mean, they saw that the lakes and the rivers were just grossly overpolluted. Grossly. Now, look at that picture that I have up there. It is in black and white. I get that. That's a fire. That fire is the river. The river is on fire. That photo, I found it online. It's the same one that's in the book. That's the Cuyahoga River in, I believe, Ohio, if I remember correctly. um, I'm sorry, I got a mental block. I have the book here. The river was so polluted, it had so many hydrocarbons sitting on the surface of it that several times a year it would catch fire. Several times. That wasn't just a one-time occurrence. Now they have since cleaned up that river, Cuyahoga, yeah, 1952. Um, They have since cleaned up that river so that doesn't occur anymore. But think about that. That's how bad things got because we just didn't recognize it back in the, in the from the Industrial Revolution up through about the 60s. That's what this whole course is about. You know, people started to wake up in the 60s, 50s and 60s going, "Wow, what are we doing? This is really bad. We're going to really, kill ourselves doing this." So the Clean Water Act focuses on point source pollution, kind of like the pipes coming out of the various manufacturing plants, but it doesn't cover the non-point stuff like farm runoff. And again, that's a whole nother tricky thing because it's hard to, because it's non-point, you can't specifically say that farmer is responsible. Um, Now, the good news is that the Clean Water Act has been very successful at cleaning up a lot of our waterways and lakes. More than double the amount of waterways and streams and everything exceed the standards in terms of how clean they are. Is it perfect? No, but it's way, way. You don't have river fires like this anymore. I mean, I saw that picture and I was just like, wow, the river is on fire. That's just weird. But that's how bad things had gotten by the 50s and 60s and into the 70s. It was just nobody noticed, nobody cared, everybody turned a blind eye. It was just about, hey, that river's there, we're gonna pump all of our crap in it and just, you know, that's what's gonna happen. And, this is what happened. Now, luckily, like I said, you can't do this anymore, which is a good thing. I mean, look at all the air pollution that thing is creating too. That's essentially an oil slick fire, probably, along with all kinds of other chemicals on top of the water. It just blows my mind. So let's talk a little bit about some of the innovative and technical solutions to sustainable water. And there's lots of people working on these problems all over the world. We have people in my department at UWM who have worked on this stuff and try to find systems that small villages can use to help purify water and things like that. Or they look at watershed management to make sure that, the overall health of a watershed is being maintained. And they do that through various types of science. And um, so there's a lot of work being done on these problems because people are very aware now that water, fresh water, drinkable water is vital to our existence. We have to have it. So here's some various solutions to the water problem, so to speak. Um, and again, this is kind of based on where you are in the world. So the first one is desalinization, which is essentially taking the salt out of salt water or seawater. So you see the image in the lower right corner. That's East. I believe that's in the United Arab Emirates. It's in the Middle East somewhere. It's a desert, right? And you have all these people living in the desert. So they spent the money, and these facilities are not cheap. You're talking billion or billions of dollars to make these. Um, but because there's so much ocean water, they essentially, once they're built, have an unlimited supply of water. There are some downsides to these too. They do create greenhouse gases, they do create some waste, but overall, it's still a better option that for some areas of the world, especially in the deserts like that, to build one of these. I've often said for years that this is what California needs, but no one wants to pay for it. And that's the problem. And the environmental people probably wouldn't allow it to happen. But if California built one of these, a lot of their water problems would probably be solved. Another thing is a new technology. It's drawing water from the air. So you can see in the upper right corner, you have sort of this big net looking thing which is sort of a condenser. So that when the fog hits that thing, that net looking thing is chilled down, and when the fog hits it, it condenses the water, and then the water is wicked away and put into a reservoir. And these have been used for a while, but on small scales because they're not cheap, unfortunately. But the technology is there, and they're starting to look into bigger scaled versions of this in areas with lots of fog. Let's say San Francisco, just to use that as an example. There's other areas too, but um, this would be a very viable option although I'm sure some people would probably disagree with the aesthetics of it, saying they look ugly. But it could be an option down the road when the technology starts to get caught up with it. Another solution on a much smaller scale that some people do actually is what's called rainwater capture. So people will get rainwater barrels and they'll capture the water that comes off their house, and they'll hold it in the tanks and then use it for things like, maybe washing other, or sprinkling, irrigation or things like that. You're not going to drink this stuff because if it's falling on your roof, it's probably full of stuff. But you can use it for other things that you wouldn't require you to use like tap water. Uh, You know, um, so, that's a viable option on a small scale. Some bigger places use it as well. Again, it's sort of that you're not going to drink it, but you could use it for other manufacturing processes, things like that. And then you have what's called gray water reclamation, which is essentially separating out municipal systems. Now, again, somebody's got to pay for this, but in theory, it would take everything that you do from the toilet and separate it from everything else. So your sinks, um, and all of that, and use the commercial waste. So if you're putting stuff, you're rinsing off dishes in your sink and you're running your dish garbage disposal, your washer and dryer water or your washer water when it comes, that's all what they call gray water. There's stuff in there, right? But it's not drinkable. It's not potable. You can't use it for anything else. But you could use it for things like irrigation, and then recycle it to put back into the toilet flushing system. Why do you need super clean water to flush your toilet, right? Who cares? It's going down into a separate system. So this has become an option as well in some areas. The problem again becomes the current water distribution centers aren't or systems are not designed for this, especially here in Milwaukee. And here in Milwaukee, this would cost a fortune to enact because we have a combined water system. Right now, everything goes down the same drain, the same pipes to the same treatment plant. And pipes are all underground, pipes are under buildings, and it would cost a fortune to create this. However, as what I think some areas are doing is when things start to fail, when they do have to go in there and replace them, they're starting to do this over time. But it's not a proactive thing, it's a reactive thing. There's also some agriculture, again, 70% of all the surface water used on Earth is used in irrigation. So there's been some techniques that have been developed to help alleviate the stresses on the groundwater systems or the surface water systems with this irrigation. Things like drip irrigation, which you can see in the bottom right corner. So these are small little rather than have huge sprinklers that just go all over the place, right? You have very focused water that's being dripped slowly down into the soil. The plants don't need all of the water at once, and if the water sits on leaves, that water a lot of times is just evaporated back up into the atmosphere. The plants need the water in the soil. That's where the roots are. So the drip technology allows the water to get exactly where it needs to be in the most efficient manner using the smallest amount of water. Now the problem is not all crops can be utilized with this, and not all farms can utilize it because some farms are massive, right? You go out to the Great Plains, you got farms that just span miles, square miles. This wouldn't be an option. It would cost way too much. You also have what's called deficit irrigation. Now you'll see that in the upper right corner. You'll notice those are grapes. Now my research deals with vineyard suitability, so I thought that was a pretty neat picture to add. I know based on my research that grape vineyards, grape plants don't like a lot of water. They just don't. That's why a lot of vineyards are grown on hills, so the water can go through and the plants will grab some of that water in their root system, but they don't like being overly wet. Well, that works perfect pretty much for this thing called deficit irrigation, where you're basically just kind of feeding it a little bit at a time, kind of stressing the plant out. But oddly enough, in In the grapes, grapes are one of those plants that actually likes being stressed. So deficit irrigation works perfectly for vineyards. And then the lastly is what's called a swale. Now a swale is sort of a shallow trench that sort of follows the contour of the land, or a berm that forces the water to flow downhill into a certain area. Now, these have been built, so you're basically creating a big mound to force the water to flow in a direction you want it to. I didn't grab a picture of this because none of the pictures I could find were very helpful. But just you're sort of altering the contour of the land in order to maximize the amount of water you're going to get in your area. I hope that makes sense. So obviously we all use water every day. So how can we reduce household water consumption? While it's not the biggest factor, I mean agriculture is the biggest user of water along with manufacturing and things like that. There are small things you can do to change it, to try to minimize your water footprint. There's that term again, water footprint. We use roughly 80 to 100 gallons of water a day. That's a lot of water. That's a lot of water. And then mostly from bathing. Sorry, I got a typo on there. And showering, washing clothes. I have a family of four. We wash a lot of clothes. A lot of clothes. I'm always doing laundry. So I don't water my lawn though. So there's a trade-off there. I never water my lawn. To me, where we live, we get enough rain. I don't need a perfect looking lawn. I to me it's a kind of a waste of water. I really don't. I'll water my trees once in a while if I'm kind of told to do that, but not very often. Things like low flush toilets. You see these more and more, and the toilet makers get it. The people who make these, they now have, you'll see them every once in a while, the ones with the two buttons. Do you need a full flush or a half a flush? That kind of thing. And where they're utilizing just enough water to get the waste away. A small thing like turning off the water while brushing your teeth. It's actually a pet peeve of mine that my kids do that. Even my wife doesn't, and it drives me nuts. It's such a small thing. It's just such a waste. I mean, I'm serious. You could waste a good gallon or two of water every time you brush your teeth, and that adds up over the course of a year. If you're brushing your teeth a couple times a day, do the math. It's a lot of water. And then, irrigating lawns and gardens, things like that, bubble soaker systems, kind of like drip irrigation, but for lawns. Um, One of the big things for this is golf courses, right? Now, my lawn is not gonna, I'm not gonna irrigate my lawn. I just mentioned that. But, golf courses use a lot of water. And where are a lot of those golf courses? In areas like, California and Arizona, places that don't have a whole lot of water. Look at New Mexico, or excuse me, Las Vegas, with all the water they have there, the big fountains and all that. So it's a weird dynamic seeing all that water in the middle of a desert. So in the book, they talked about this concept called WASH. And what WASH is water and sanitary and hygiene. It's sort of the three principles of making sure that even areas that don't normally have water available to them start to get them, to try to even out the inequities of, like we have an abundance of water here, but you go into sub-Saharan Africa and they have much larger issues. So that's why this whole thing with the water, the sanitation and hygiene has become one of the highest priorities for certain parts of the world. Again, 2.5 billion people, I mentioned this before, don't have um, access to toilets and latrines, which creates huge biological waterborne disease issues. Some of them are inexpensive, simple and inexpensive solutions. Some, obviously would require more money, and that's not always an option. But one of the things that, when dealing with these types of things, is again going back to, you have to have the buy-in. The people who are going to use these technologies have to buy into the concept. And then you have to be able to scale it up. And I'm going to explain this image that you see based upon these principles. So the scale of the implementation has to be applicable. You can't tell a tiny little village out in some country in Africa, hey, you should build this huge desalination plant that costs $1 billion. It's not going to happen. You have to kind of start small and make sure the people that are using these solutions understand their benefits and like the last bullet point, they have to take ownership of them. They want to use this to ensure success and then implement it and then continue to train people on it. So you'll see these blue looking things. Um, those are essentially, you've seen pictures before of, African villagers carrying water buckets on their heads. Well, those buckets can only be so big. Water's heavy. Water's like 8 pounds a gallon, right? It's not light. So somebody came up with an ingenious idea. Instead of carrying the water, why don't we push them? So they created these barrel looking things. They go and they fill up these blue barrels. You can see the barrels here and on the left. Here's a barrel, and then there's a lid here. You can see kind of right there with the orange. So they could fill these up, and rather than carry them, they just push them. Which, yeah, I'm sure is not easy, but it's a lot easier than carrying them. And because they're bigger than your normal water bucket, they can make fewer trips and get more water at a time. So here's a small, simple solution, pushing the water as opposed to carrying it. Now, these things are being used all over the world now. They've been shipped out to all kinds of little villages and countries all over the world because it's such a simple, ingenious solution to a problem that is very common in developing nations, or in just, let's be, third world countries, so to speak. So these simple solutions play a huge role once those last three bullet points are taken into account. They got to be inexpensive. The people have to buy into them. It has to be applicable at a scale they can use, and they have to want to actually do it, take ownership of it, and then train others on how to do it. If they follow those sort of guidelines, all of a sudden now you go, wow, their lives probably got a little easier because they don't have to make as many trips to the water hole, and because they can carry more, and it's just, life becomes at least a little bit better in that regard. So there's also some ecological approaches to sustain aquatic resources, right? And we talked about these, so I'm going to kind of just gloss over them a little bit. Watershed management is making sure you reduce habitat degeneration and non-point pollution. So I already mentioned these, right? Watershed management has to look at where are the farms, where is the pollution coming from that's non-point source, and making sure that the habitats both within that area and outside of that area are maintaining things like wetlands. That's the next one, wetlands restoration. Don't get rid of the wetlands. Let's expand them, protect them, so they can play their vital role in filtering out pollutants and getting the water back into the groundwater system. Another thing, a small thing, is what are called riparian buffers. And all that means is that you're creating sort of an area, let's say, 300 feet on each side of a river. And okay, so you have a river, you measure 300 feet this way or 300 feet that way, and nothing can be built within that 300 feet. And what that does is that sort of protects the natural lay of the land. It protects the habitats within that stream zone, so to speak. That's what a riparian buffer is. These are very common now. You probably don't even realize it. But when let's say a new subdivision is going in and things like that, they have to take all this stuff into account. Another one is removing dams. Okay, dams, you're not going to remove the Hoover Dam necessarily, but there are a lot of small dams. I did a small project with some people that were doing just this, trying to remove any blockages. Now, when I say dam, that doesn't have to necessarily be man-made. It could be naturally occurring, a tree falling, rocks falling, something like that. But no matter what, it's creating a barrier for things like fish to go upstream and spawn. It's creating a barrier that could um, uh, create a sediment trap where you have all these sediments that just stay right there, that could ultimately alter the where the stream flows, creating other issues, flooding, things like that. So, dam removal, at least, the ones that can be removed, and a lot of them have been around the country, play a huge role in maintaining these aquatic resources, things like rivers and all the critters and plants that live around them. And then finally, there's a water crisis. Not necessarily everywhere, but in many parts of the world, there is a water crisis. And even in this country, as good as the water's become in the last 40, 50 years, there's still a water crisis. There's still a lot of pollution that needs to be cleaned up. Now, if you take America out of it and start looking at some of the other, poorer nations, there's a lot of issues going on here. A lot of diseases that could be wiped out strictly because by having a clean water source. That's what that WASH stands for: water and sanitation and hygiene. With those three things in place, all of a sudden the life gets a little better. You have less disease, less mortality, especially among young children. The problem is the poor nations can't pay for it, right? They don't have the money, they don't have the tax base. And that's essentially what it is. Here in America, everybody pays their taxes and things get done at the federal, state, and local levels with all the taxes we pay. Um, to things like roads and infrastructure, schools, all of that gets paid via our taxes. Well, if you don't have people making money in your country, there's no tax money to be had. So they don't have the money to do this. So there's a lot of groups out there, global aid and public and private groups, that are helping improve this WASH idea, the water, sanitation and hygiene, trying to get those things eliminated or alleviated, at least in some of the poorest areas of the country. This isn't going away. It's just not something you're going to see on the news or anything like that. But it is a real issue in many, many parts of the world. All right, so that's it for chapter 4. There's some really interesting concepts in this chapter in terms of not only the issues that are taking place that seem to go unseen all the time, right? We go eat corn, right? If you like corn on the cob. Well, that corn comes from a field, and that field has probably at some point been sprayed, and that spray has probably been washed off into a stream. So we're all part of this. It's not any one person's fault. Okay? You can't place blame. All you can do is to try to do things better. The only blame is when you get to point source pollution, where that pipe is coming out of that building and it's too dirty to be being put in our river systems. That's a different story. So hopefully you can see from this, there's a lot of things that are being done that still need to be done, and even small things you can do to help with the water crisis. Now turn off that water when you're brushing your teeth, all right? So the next chapter is chapter 5, which deals with agriculture and the food that we eat, and that should be interesting as well. I'll get working on that soon as well. So hopefully you learned something in this chapter, and I'll see you in the next one. Take care.